Hi, welcome back. This is Calc 2, continuing on with Chapter 8. We're going to look at numerical integration. So if there's a particular integral that maybe you can't do by hand, you can't find a nice antiderivative to evaluate, you can always use techniques called numerical integration techniques. And we'll take a look at two techniques, and we'll go and take a look. Okay, so the first technique is the trapezoid rule. So it's similar to the way the Riemann sum would work, okay, before you take the limit. Trapezoid rule. So the deal with the Riemann sum is that you could kind of approximate the area underneath the curve with a bunch of rectangles, right? So we would have some area we're trying to figure out, and then we would kind of populate it with a bunch of rectangles, maybe here using the left-hand endpoints for the tops of the rectangles, blah, 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 on and on. And then you get this, except we're actually going to have, I guess in this case, we'll actually populate it with all the rectangles. So we could, without taking the limit, without thinking in any way like that, we can get an approximation for the area underneath this curve by just summing up the area of these rectangles. So if this is f of x, the area would be approximately the sum of the heights times the bases from I equals 1 to how many there are, n of them, right? Okay, so the trapezoid rule is kind of just making a better box, so to speak, for the area, right? So right now, as it sits, the area formula for this particular rectangle a sub I would be the height of the rectangle times the base of the rectangle, base times height. The trapezoid rule, instead of using little rectangles, what we're going to do, so this is like a before for our approximations. Now, for our approximations, we're going to use trapezoids. Okay, so it's the same kind of picture, your Riemann man, quote unquote Riemann man. Now he's like a trapezoid man. He's going to run across and pick up the areas of all these trapezoids underneath the curve. Okay, so here's our curve again. I want to approximate the area underneath it. So what I do is just section it up into a bunch of little subintervals. And this time, instead of using boxes or rectangles, I use trapezoids. So note the top of the box. Okay, it's basically a straight line where the endpoints are actually on the curve. Okay. And the Riemann man will run across and figure out the area of each particular trapezoid, and that will approximate the area. And you can see, it seems like at least this is going to be a better approximation than the rectangles, right? Because in the rectangles, you can see there's error all over the place. There's a lot of error there, a lot of error here. Here you're going over, you're going under approximating, maybe under approximating, under. Okay, so there's a lot of error there. But in the trapezoid case, the trapezoids conform better to the actual curve. Okay, there's still error, but it's not as bad as just using rectangles. Okay, so how are we going to pull this off? Well, in this case, we need a new formula for the area of a trapezoid. And if you've forgotten, the area of a trapezoid is basically 1/2 height 1 plus height 2. So if we have, just let me extract kind of one of these trapezoids and take a look here. So the traditional formula you learn in geometry for a trapezoid, you'll have this height A, this height B, and then the base H, and then the area will be H over 2 times A plus B. Okay, we need to translate all of that into terms of f of x and basically widths here in the bottom, these change in x's. Okay, the change in x equals So if this is our beginning A and our end is at B, change in x will be B minus A over the number of trapezoids. So in this case, we have 1, 2, 3, 4, 5 trapezoids, so you put 5 down there. But in general, change in x, just let me write this maybe over here to the side. So in general, change in x is B minus A over n. Depending on the number of trapezoids you want to use. Of course, you use more trapezoids, you get a better approximation. Okay, so, right. Then our area will be, for one particular trapezoid, we want to rewrite this in terms of, and I'm just talking about one particular, not the total sum of the areas. The area of a particular trapezoid in terms of f of x and all that junk is going to be the base, which is change in x all over 2 times a plus b. And for those, we're going to have to basically use endpoints. So maybe for this point here and this point here, like this first point would be something like x sub I minus 1. And this point here we'll just call x sub I. Okay, starting with A equaling x sub 0. So you still have to kind of think of it in terms of general pictures, but it'll be x sub I plus x sub I minus 1, right? Or vice versa, if you will, and it's f of that, because we're dealing with heights. Okay. Right, so the running man, the trapezoid man, in this case, as he goes across, and we could think of this particular scenario here, right? So it's the sum of these a sub i's, which will approximate the overall area, which I'll just call A, will be the sum of 5 of these areas. So we're going to have, what, change in x over 2 times f of, and I'll start at x sub 0, okay? So we'll call A is x sub 0, and then this one is x sub 1. I'm sorry, I'm making the picture just a mess. This point here is x sub 1. This point here, I know I already called it x sub I, but that's just in general. X sub 2 for us, and then x sub 3. And then this point, x sub 4. And then finally, B will be equal to x sub 5. Okay, and we just want to see what happens when we add this up. So I have f of x sub 0 plus f of x sub 1 for the first trapezoid, plus change in x over 2 times the next trapezoid. So there's kind of an overlap of the points. So the first, the base on the first trapezoid, the left endpoint was x sub 0, the right was x sub 1, right? Then when you go to the next trapezoid, the left is x sub 1, so you'll have f of x sub 1, and then the right will be f of x sub 2, right? And then plus, and that's, what do we have? We have a sub 1, a sub 2, and then let's just go dot, dot, dot on these dudes, right? Well, I guess we'll do them all. Why not? It's not like I'm running out of paper or something. A sub 5. Right. So plus change in x all over 2 times the next, the base of a sub 3, is a sub 2 plus a sub 3. So we need f of x sub 2 plus f of x sub 3. And then plus change in x over 2 times f of x sub 3 plus f of x sub 4. That would be area 4, and then plus finally area 5, change in x over 2 times f of x sub 4 plus f of x sub 5. Okay. Let's clean that up, right? So first we note, all right, I can factor out a change in x over 2, right? No issue there. Change in x over 2, great. What does that leave me with? That leaves me with f of x sub 0 plus f of x sub 1 plus another f of x sub 1 plus f of x sub 2. So you can kind of see, I got this guy, I got this guy, and then there was another one of those, and then I got f of x sub 2, that's where I am right now, plus another f of x sub 2, plus f of x sub 3, plus another f of x plus f of x sub 3. plus f of x sub 4 plus another f of x sub 4, and then finally plus f of x sub 5. I should have used like n equals 3 or something, but okay. So what's happening there? Well, there's this bunching, right? There's 2 of these, 2 of these, 2 of these, 2 of these, and then on the ends there's 1 of those, right? So there's this weird bunching phenomena that happens, and kind of our final form seems to be f of x sub 0 plus 2 f of x sub 1s plus 2 f of x sub 2s. And this is a pattern you're going to see whenever you do this rule. Okay, it's going to be 1 and then a bunch of 2s, and then the last endpoint will get you back to 1. Okay, this should be x sub 4. No, let me fix that, make it look pretty. Okay, so there's that. So what? Well, that gives us a formula, and the formula is theorem 5.17. So in general, if f is continuous on the closed interval from a to b, we can approximate the area underneath that curve, or approximate the area, or we can just say approximate that particular integral. So let me just write that integral. The integral from a to b of f of x dx with the following formula, b minus a all over 2n, and the b minus a over n is change in x, right? So, you know, it's this thing, that thing that I just wrote is that thing. Change in x over 2 is the same as b minus a all over n all over 2, which will be this thing. Okay, so there's that factor, and then on the inside you'll have f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2 plus blah, 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 plus 2 f of x sub n minus 1, and then plus 1 f of x sub n. Okay, where n is the number of rectangles you're using. Or in this case, trapezoids. Okay, so let's try doing one of these with a function that we know the antiderivative. So the advantage of this is that you don't need to figure out the antiderivative, and there's going to be functions that are just nightmares to figure out antiderivatives of. That's kind of what we'll handle. But in the beginning problems, we'll just look at ones that we already know how to integrate. That way we can compare our answer with the approximation. Okay? So they want you to approximate the integral of x cubed from 0 to 2 with 4 trapezoids, n equals 4. Okay. So the formula, right? So I have 2 minus 0. That's a minus. So a is equal to the bottom limit on the integral, and then b is equal to the top limit on the integral. So the 0 is on the bottom, and then 2. Then we have n is 4. So b minus a is 2 minus 0 all over 2 times n, which is 4, times what is the f of x? Well, that's just the thing inside the integral. So this is f of x. Okay? That is our f of x. And then what are we putting inside the f of x's? Well, you have to go to your number line if you need to and kind of partition it into 4 intervals, right? So you're starting at 0 and going to 2. Your change in x is b minus a all over n, so that's going to be 1/2. So you just move by 1/2. So 0 plus 1/2 is 1/2. And then you have 2 halves, and then you have 3 halves, and then you have 4 halves. Of course, that would be 1, 2, 3, 4 trapezoids you'll have. Okay. Okay. Right. So then we're plugging these numbers in to f of x, right? So I'll have f of the first point, 0. So f of 0 plus 2 f of, and then you plug in 1/2, right? And then plus 2 f of 2 halves, which of course is just 1, plus 2 f of 3 halves, and then plus 1 f of 2. Okay. Okay. So we're going to have 2 all over 8, which is the same as 1 over 4 times, and I'm plugging all of these numbers into my f of x, right? So 0 cubed is just 0, plus 2 times 1/2 cubed, which is 1/8, plus 2 times 1 cubed, which is 1, plus 2 times 3 halves cubed, which is 9/4, plus 1 times 2 cubed, which of course is just 8. Okay. And we could probably do this without a calculator, right? So 1/4, what do we have inside here? Is 2/8 is 1/4. Plus 2 plus 8 is 10, plus 18/4 is going to give me 1/4 times 19/4 plus 40/4, which is 1/4 times 59/4, which of course is 59 16ths. And so let's get an approximation of that. 59 divided by 16 is, I screwed up. What did I do wrong, folks? 3 halves cubed is not 9/4. It is 27/8. I apologize. Okay, so that'll change things just a little bit. 27/8 times 2 is going to give me 27/4 right there. So hope everything else is good. 27/4, and then that'll give me 28/4 here. And that'll give me 68/4. Does 4 go into 68? Yeah, 17 times. So it'll be 17/4. And then that should be 4.25. Okay. Of course, we want to compare this to the actual answer, which we can get via the antiderivative. So we have x cubed from 0 to 2 dx. We have x to the 4th over 4, 0 to 2. 2 times 2 is 4, so those will cancel, and then you just get 4. 4 minus 0, of course, is 4. Okay, so it's an overestimate in this case, you know, bummer, but it's in, you know, if you can't get the answer, that's one way to do it. It gives you a way you could code that probably pretty easily. Okay, the next kind of method is Simpson's method, or Simpson's rule. And in this case, instead of using rectangles, what we're going to do is kind of use quadratic functions. Okay, so you're going to kind of take whatever interval you're working with and dissect it into thirds, okay, like this. And then you're going to thread a little polynomial through it, okay, and the quadratic polynomial that goes through these 3 top points, here, here, and here, okay. So maybe a quadratic that looks something like this, that will conform pretty well to the function. And then you just find the area underneath that polynomial, and you're kind of, you're going to be good to go. So you're basically finding the area under a bunch of polynomials and using that to approximate the area underneath the curve. So, you know, you can, if you needed to extend this a little bit, you can get maybe another triplet here, here, and here. And then you're for that interval, you're kind of finding the area maybe underneath this parabola. Okay. And we have formulas to do that. So that would be that first area, and then we would get kind of this red area in the second interval. Okay, the construction of the kind of formula, like before we had the 1, 2, 2, 2, 2, 2, 1. The construction is a little more complicated. It's all based on the fact that if you are integrating a polynomial, like integral p of x dx from a to b, you can figure this out by just kind of using a shortcut formula, b minus a over 6 times p of a plus 4p of a plus b over 2 plus p of b. Okay, so why is this good? It's because you can replace the polynomial with any function you want, and you don't really need to know its antiderivatives. You could just say the polynomial f of x dx from a to b is approximately b minus a over 6 times f of a plus 4f of a plus b over 2 plus f of b. And that's kind of the magic of it. So if you were to kind of do that, you're going to end up with this formula and then some bunching, like we did up here with the f of x sub 1 plus f of x sub 1. Okay, because now you're going to have kind of triples, right? You're going to go like f of x sub 0 plus 4f of x sub 1 plus f of x sub 2, right? And that would be your first kind of triplet. And then you would go plus f of x sub 2 plus 4f of x sub 3 plus f of x sub 4. Right, so you would get these guys bunching and so on. So the pattern is always on these functions is always going to be 1, 4, 2, 4, 2, 4, 1. Okay, and in general, I'll just give you the formula, and if you want to get more involved, you can read the explanation in the book. But in general, you know, given a continuous function and all that jazz, we can approximate the integral from a to b of f of x dx with the formula b minus a all over 3n this time times f of x sub 0 plus 4 f of x sub 1, etc. Okay, so let's then go ahead and try a Simpson's rule on one of these. So this will be another example. It used to be in the book. Integral from 0 to 2 of x ln of x plus 1 dx. Okay, this integral is a little harder, but I think you could probably do it by parts if you wanted to. Let's do it using Simpson's rule anyways, just for the sake of, you know, learning something. So this time again, I'll just use 4 sections underneath the curve. If you use, you have to be a little careful with Simpson's rule. I think you always have to use an even number of subintervals. I can't say trapezoids or rectangles. I have to say, just kind of subintervals with polynomial tops. But yeah, it's something weird like that. Because of the way the pattern is, you always have to use like an even number, I think. But you can look that up if it ever becomes an issue. Anyways, let's take a look. So using Simpson's rule, we have b minus a. So we can get some information, right? A is 0, b is 2. Change in x is b minus a all over n, which in this case is 4. So change in x is 1/2. To get our endpoints, you can kind of do your number line 0 to 2. So go by 1/2, 1/2, 1, 3/2, and then 2. So we'll have b minus a, 2 minus 0 all over 3 times n. So in this case, it's 4. And then times, now we start with the f of x sub 0, right? So we have f of 0 plus 4 f of 1/2 plus 2 f of 1 plus 4 f of 3/2 plus the last one, right? So f of 2. Okay, so what do we have? 2 all over 3/4, 2 all over 12 is 1/6. And then our f of x function is just the thing inside the integral here. Okay, so I'll have f of 0 is just 0 plus 4 times, plug in 1/2, so I'll get 1/2 ln of 1/2 plus 1 is 3/2 plus 2 times 1 times ln of 2 plus 4 times 3/2 ln of 5/2 plus 2 ln of 3. Okay. And then probably what I'll do is here go to like Wolfram or something and just plug it in there and see if I get a nice little answer. Okay. Make sure I can see the whole thing. Yeah. All right, so Wolfram is probably already. Oh, no, you didn't. I hate my freaking Wolfram alpha. So Wolfram is some dude from Caltech. He started something called Mathematica, and then later kind of branched out into this more generalized and intelligence machine, Wolfram Alpha, which I just use as my calculator online. Okay, so I'm going to go 1/6 times 0 plus apparently 2 ln of 3/2 plus 2 ln of 2 plus 2 goes in 4 2 times 3 is 6 ln of 5/2 plus 2 ln of 3. And I'm getting about 1.6 something. We'll go the 4 decimals. Okay, so 1.6487. Okay, let's see what the actual state-sanctioned answer is in Wolfram. Int of x star ln of x plus 1, comma, x goes from 0 to 2, enter. It's too hard, I can't figure it out. 1.6479. Pretty close. Okay, interesting. Let's do one that we actually can't integrate, right? So let's see the power of that. And something we're not going to be able to integrate And this is going to be the video quiz question, by the way. So video quiz, video quiz, video quiz. Wake up. You know. The integral of e to the negative x squared. Okay. So this is an important integral because the area underneath it is usually used in probability. And when we integrate it, look at that. You don't know what that is. We don't know what it means, right? So, right. It turns out there is a kind of a clever way to figure out these kind of integrals, but you won't learn it until you get in the multivariable, if they teach you there. If you don't watch that Polar Pi video, that dude does it in his videos, but you need Calc 3. But he's pretty good at explaining stuff, so if you didn't take Calc 3, he'll probably explain it to you. After you get through the polar section, chapter 10, you'll be kind of better at understanding that. So there's some polar baloney we got to take care of before we can get you there. But anyways, yeah, this sort of thing, we can't find the antiderivative of it, right? Us Calc 1 students don't have any way of doing that. So if we wanted to figure out, for example, the integral from 0 to 1 of e to the negative x squared dx, that would be kind of difficult. They don't know because they don't know how to get the antiderivative. All right, so we can use the trapezoid rule or Simpson's rule in order to figure this out. We're going to do one of each, and we should get about 0.7468. Okay, so let's see if we can do that. Okay, so let's get kind of our information first. So A is 0, B is 1. We'll just use N as 4. Okay, let's not get carried away. What else? Change in x then will be B minus A all over 4. So that'll equal 1/4. If you want your interval, we're going from 0 to 1, and we're going by 1/4. So 1/4, 2/4, 3/4, 4/4. And I think that's all the information we really need to get through this issue. So let's do the trapezoid first. Okay, so trapezoid rule is change in x all over 2. So we have 1/4 divided by 2 is the same as 1/4 times 1/2. And then we're going f of 0 plus the patterns 1, 2, 2, 2, 2, 2, 1. Okay, so 2 f of 1/4 plus 2 f of 2/4 plus 2 f of 3/4 plus 1 f of 1. Okay, and that'll be 1/8. Let's go ahead and plug our function in. So our function is e to the negative x squared. Okay. So e to the 0 plus 2e to the negative 1/16. 1/4 squared is 1/16 plus 2e to the negative 4/16 plus 2e to the negative 9/16 plus 1e to the negative 1. Okay. And we could plug that into our calculator. I will dispense with the pleasantries and just give it to you. So it is 0.7430. Okay. So in this case, we can go look online. 0.74 something? Yeah, so it's kind of close. Let's look at the trapezoid version. Or sorry, the Simpsons version. So this time it's change in x over 3. And then the pattern is 1, 4, 2, 4, 2, 4, 2, 2, 4, 1. Right? So we have f of 0 plus 4 f of 1/4 plus 2 f of 2/4 plus 4 f of 3/4 plus f of 1. Okay. And of course, we just basically have the same kind of formula, 1/12. If you already got it in your calculator, you can just go back and edit it. So e to the 0, you just have to change the coefficients, right? 4e to the negative 1/16 plus 2e to the negative 4/16 plus 4e to the negative 9/16 plus e to the negative 1. You see, it's really, really similar to the trapezoid. It's just you have 4 here and a 4 here, and then the leading fraction is a little bit different. Okay, so is it better or is it worse? And it turns out, at least in this case, it's better. I think in general it's better. But I'm sure you can find exceptions to that rule. 0.469er. Okay, great stuff. Okay, so that was the quiz question, video quiz question number 2 and homework number 5. And we will see you next time.